Right. Oh, sorry. Okay, maybe.
No, it has disappeared.
No, wait a second, because I have two screens. Oh, something.
No, no, it has disappeared.
Now it appears again.
No,
What about now?
no.
Ah, sorry. Désolé. J'ai. What about now?
Yes. Now it's fine.
Okay.
Okay. Yeah. Yeah, yeah. Okay.
Yeah.
Okay, so maybe we can start.
Yes,
Okay,
absolutely.
so now we have the pleasure to listen to Abdenacer Makhlouf from Université de Haute-Alsace à Mulhouse. So he will speak about Jacobi-Jordan algebras and Jacobi-Jordan conformal algebras. Please.
Thank you very much, Dominique. And I would like to thank the organizer for the invitation to give this talk. I am going to discuss plenty of non-associative algebraic structures, among them this Jacobi-Jordan algebra and some related structures, and also Jacobi-Jordan conformal algebra. Then this is the outline of my talk, and this talk is based on several papers, three of them mentioned here. It's a joint work with Amir Baklouti, Said Benayadi, and Sabri Mansour, and also with Chtioui and Mabrouk. Let me maybe start with a small introduction about this Jacobi-Jordan algebra, which appears under different names, and in fact, it's just the Jacobi condition, and instead of having skew symmetry on the bracket, we are going to consider commutativity on this bracket. And this is called by many people Jacobi-Jordan algebra. We will see later why Jordan is attached to this structure. And you can see the names using this terminology. And you can find it also under the name of Lie-Jordan algebra by Camilla, and Pasha Zuzmanovic call it Mock-Lie algebra. Okay, what is a Jacobi-Jordan algebra? This is just a pair. It's a non-associative algebra consisting of a vector space here G and a bilinear map denoted by a dot here. And this multiplication satisfies the commutativity condition and the Jacobi condition, which is written here. One small example is this: if you take a vector space of dimension 4, and you take E1, E1 is E2, and E1, E3 is E4, and of course commutative, and then this multiplication satisfies Jacobi condition. Okay, now some properties. Then we can also we can see that this Jacobi-Jordan algebra is in fact our particular case of Jordan algebra. Let me just remind you what is a Jordan algebra. This is a commutative non-associative algebra satisfying this condition. Okay. Then this observation by Baeza and Burt is that any Jacobi-Jordan algebra is a Jordan algebra. In fact, it's a Jordan algebra which is nilpotent. So that is, it satisfies x to the power 3 is 0. In fact, we can also characterize that Jacobi-Jordan algebra as a non-associative algebra which are commutative and satisfying x to the power 3 equals to 0. Now, what about representation and models of this type of algebra? Then we can define in two different ways these structures. First, if we start with G Jacobi-Jordan algebra, a left Jacobi-Jordan G model, then this is a vector space equipped with a billionaire map from G times M to M, satisfying this condition. In fact, if you have a Lie algebra, then you have plus here, then you can see that minus signs appears here, then they will appear last in this talk. And just similarly, we can also define a representation to be now a map, a linear map from G to the endomorphism of M, and satisfying this condition. This is the two concepts, but this is G model and a representation of Jacobi-Jordan algebra. And in fact, since I said that this Jacobi-Jordan algebra are Jordan algebra, one can also uses the notion of representation introduced by Jacobson. Then in fact we can recover this just by replacing P by minus P, and we get the notion of representation as defined by Jacobson for Jordan algebra, that is the map P from G to the endomorphism of M, satisfying this condition 3. And now back to the two concepts I defined just before. In fact, representations of Jacobi-Jordan algebra or G models just are two different ways of describing the same structure. In fact, there is an isomorphism of categories between the category of the G models and the category of representations of G. Then we can characterize this one-to-one correspondence by setting that P of X of A, this is just X star A, where star is the action. In fact, we can also characterize this representation using semi-direct product. In fact, if the pair PM or MP, where M is a vector space and P the representation of G, this defines a representation on the Jacobi-Jordan algebra. This happens if and only if the direct sum GM is endowed with the Jacobi-Jordan algebra structure defined in this by this multiplication. Then we have this correspondence with semi-direct product, as usual. Now, what about the derivations in this setting? But in fact, we can also define anti-derivations. Then let's start with an algebra G and the homomorphism D from G to G. Then this it is a derivation, and as usual, if it satisfies this condition. Now we will say that this is an anti-derivation if it satisfies this condition. In fact, the difference is that here we have minus and here minus as well. Okay, then this is the concept of anti-derivation. That we in the sequel we will denote by der G the vector space of all the derivations of the algebra G, and there the space of anti-derivations. Now, if we start with Jacobi-Jordan algebra, if you consider the map xy, this adjoint map xy defined by xy, then this is an anti-derivation. Well, that's why we introduced this concept of anti-derivation. This is an anti-derivation, not a derivation as in the case of Lie algebra. And again, if we consider now two anti-derivations, Now, if we deal with an anti-commutator, not the commutator, I mean the anti-commutator with the plus commutator here, then this bracket d prime defined by d prime plus d prime d, this is an anti-derivation, but not for in all cases, but only if and only if we have this combined condition satisfied. Then we need some condition here. Okay, now we are going to discuss Jacobi-Jordan admissible algebra, which means the non-associative algebra that lead to Jacobi-Jordan algebra. First, let me introduce for non-associative algebra this the commutator, the usual commutator, which is defined here by bracket, and by this brace we define the anti-commutator. And here we consider the associated algebra with brace, which we denote by A plus, and the associated algebra with bracket we denote by A minus. Then if I start with a non-associative algebra A with a dot, then it is called Jacobi-Jordan admissible algebra if A plus is a Jacobi-Jordan algebra. And of course, we say that we have a Lie admissible algebra if A minus is a Lie algebra. Now we are going to discuss and characterize such non-associative algebra that lead to Jacobi-Jordan admissible algebra. Now, for Lie algebra, we use a lot the associator, because you know that if you have an associative algebra, by the commutator you get a Lie algebra. In fact, here we need an anti-associator, and the first example of Jacobi-Jordan admissible algebra are the anti-associative algebra. Anti-associative algebra means that this condition is zero. No, I mean this. We have this condition that is if you change your bracket, if you're bracketing like this, you have to add minus here. And then this motivate the introduction of an anti-associator. Then an anti-associator is a trilinear map, which is defined in this way, with respect to a multiplication dot. And this is x dot y, that's z, plus x dot y, that's z. This is the anti-associator. Now, if as first observation here, if you have an anti-associative algebra, that is an algebra satisfying this condition, then if you take the plus commutator or the anti-commutator defined in this way, then the G with this circle multiplication is a Jacobi-Jordan algebra. Then we can say that an anti-associative algebra or all anti-associative algebra are admissible Jacobi-Jordan algebra. Okay, now we are going to introduce some classes of different other classes of Jacobi-Jordan admissible algebra. Let us consider first non-associative algebra A, and we are going to deal with this symmetric group S3. Then we say that we have we define G anti-associative algebra if this A dot is a G anti-associative algebra if the sum over all the elements of G, here G is a subgroup of S3, this sum of the anti-associator of x sigma 1, x sigma 2, x sigma 3, this is 0. This was introduced for Lie algebra by Gauss and Rennes. Now we generalize it here. We consider it here in the case of anti-associator. And we now here we have something new, which is we are just going to define six elements of K and scalars, which we denote by lambda sigma, and sigma here is an element of S3. Then we consider this set of six elements of six scalars, and we assume that this six scalars, the sum of these six scalars is different from zero. Then we say that with respect to this set lambda, we say that A dot is a lambda anti-associative algebra if this sum, the sum of over lambda sigma of the associator, when the sigma runs on S3, then if this is zero. Then here some observations. We notice that if you have a G anti-associative algebra with a G is the subgroup, then there exists lambda a set of elements. There always exists a set lambda of six elements that such that this sum is different from zero, and such that this A dot is a lambda anti-associative algebra. Which means that this lambda anti-associative algebra includes G anti-associative algebra I mentioned before. We can also normalize somehow this class by saying that if we have a lambda anti-associative algebra with respect to some set lambda of scalars, then this is equivalent to a beta anti-associative algebra where we have a set of scalars satisfying that the sum is 1. Here we assume that the sum is different from 0, but here we can normalize and take a sum which is equal to 1. Now, in order to characterize this Jacobi-Jordan admissible algebra, we first notice that the fact that A dot is a Jacobi-Jordan admissible algebra, this is equivalent to A dot is an S3 anti-associative algebra. You just write the condition, and you can notice that there is this equivalence. But now I'm going to give the result which characterizes Jacobi-Jordan admissible algebra. First, since we need this 3-power anti-associative notion, let me just define this. Then if we have a non-associative algebra A dot, it is said to be 3-power anti-associative if we have the anti-associator of XXX, this is 0. And now we have this result with Baklouti and Benayadi and Mansour characterizing this Jacobi-Jordan admissible algebra. In fact, A dot is a Jacobi-Jordan admissible algebra if and only if it's a 3-power anti-associative algebra, and if and only if it's a lambda anti-associative algebra where lambda is a set of scalars such that this is different from 0. Then this is an interesting characterization which we have for Jacobi-Jordan algebra, but we don't have for Lie algebra, for example. This equivalence, equivalent to 2, doesn't hold in the case of Lie algebra. Indeed, we have an example. We can consider this 3-power. If you have a 3-power associative algebra, this always leads to a Lie algebra, but the converse is not necessarily true. For example, if we take this Brillouin or left symmetric algebra, defined by this multiplication, then this is a Lie admissible algebra, which is not a 3-power associative algebra, because we have z times z times z. This is different from this. Then this is stronger than Lie algebra somehow. Now we are going also to provide some corollaries and observe that we can recover some results, for example, observed by Bourdet, I mentioned in the beginning. Then A dot is a Jacobi-Jordan algebra if and only if it's commutative and x power 3 equals 0. Then we can recover it from the previous result here. And we can also maybe define some nice classes one can consider and discuss. Then I mentioned that the Jacobi-Jordan algebra are lambda anti-associative algebra where the sum of the coefficient defining this lambda is different from 0. Then, for example, one can define in this case what we called pre-Jacobi-Jordan algebra. Then this is then the identity for this pre-Jacobi-Jordan algebra is that the anti-associator of xyz plus the anti-associator of yx z. This is 0. This is the left pre-Jacobi-Jordan algebra, and they are Lie admissible. And of course, similarly, one can define right pre-Jacobi-Jordan algebra. We can also define alpha beta pre-Jacobi-Jordan algebra with the sum different from 0. And here is a generalization of the previous one. Here you have just to consider, here you can consider identity where you can put alpha here and beta here, such that the sum of these two coefficients is different from 0. And this is, we call this class alpha beta pre-Jacobi-Jordan algebra. It generalizes the previous one. And we can also simplify this and define a Q pre-Jacobi-Jordan algebra by the ones satisfying the anti-associator of xyz plus Q anti-associator yxz equal to 0. Of course, for Q equals 1, this is just the pre-Jacobi-Jordan algebra. Okay, then this is about this Jacobi-Jordan admissible algebra, some classes, but we can also define what we are going to call a mutation, alpha beta mutation of a Jacobi-Jordan admissible algebra. If we start with a Jacobi-Jordan admissible algebra and alpha beta two scalars in K, then you can define the new product in this way, which is a bracket here, which is some weighted anti-commutator by alpha beta. Then this new bracket defines a new Jacobi-Jordan admissible algebra, which we call alpha beta mutation of the previous Jacobi-Jordan admissible algebra. Now we are going to switch to cohomology, where we are interested in the cohomology of Jacobi-Jordan algebra. I told you that this Jacobi-Jordan algebra are Jordan algebra. And it is well known that we don't have a cohomology for Jordan algebra. This is still an open problem. But here we are going to define a very special cohomology. We call zigzag cohomology for this Jacobi-Jordan algebra. And it turns out that this cohomology is helpful for deformation theory and for extensions. What we need to define a cohomology, we need quotients. Then here, we fix first our Jacobi-Jordan algebra G, and M. This is a vector space. Then what will be called a quotient here? This is just a map from G times G times G and time for n quotients into M. And this quotient is symmetric if we have this condition satisfied, and it is skew symmetric if we have a sign here when we apply this permutation sigma. Then we denote by, in the sequel, we are going to denote by Ln Gm, the set of all n linear maps from G to G, G tensor G n times to M. And S and Gm, this is the symmetric, this will be the symmetric quotients. And the skew symmetric or the anti-symmetric ones, we will denote them by A and Gm. And for n equals 0, then this L0, this is the same as 0, and this is the same as A0, and this is just our vector space M. Okay, now we are defining two sequences of operators here. This is what will be considered to define this zigzag cohomology. In fact, if we have a sequence of operator Dn, then D0 from L0 to L1, D1 from L1 to L2, etc. And we have another sequence of operators, which we denote by delta. Then delta 0, again here it goes from L0 to L1, etc. In fact, in order to define our cohomology, we are going to restrict the definition of the delta n only to anti or skew symmetric quotients. Then delta n is just defined from an to ln plus 1. And for all this, for d and d delta, d0, this is just px of m, px times m. Here, of course, m is considered to be a representation of G. And how is defined is D? Then D is defined in this way, using the representation P. This is the quotient C. Here is a map from L, L tensor L, or L times L, P time. Then this is the definition. This is the definition of D P, and this is the definition of delta P. And you can notice the difference here. The difference is just this sign. Then here we have plus. It's almost the same the expression. Here we have plus, and here we have minus with delta. And again says that here delta is just defined over anti-symmetric or skew-symmetric quotients. And what is true? Of course, we don't have dp composed with delta dp minus 1, but what is true is that dp composed with delta p minus 1 is 0. In fact, we need only antisymmetric. In fact, here we apply this to antisymmetric quotients, and for any p, this is true. Then now, with respect to this, we can define space of p cocycles, and this will be just the kernel of dp as usual. And we call this zigzag cohomology, and we put this z here to say that this is zigzag cohomology. And what will be the space of p coboundaries? Then this is the set of LP, of element C in LP, such that there exists C dash in AP minus 1. This C dash is anti-symmetric. And then this C and C should be equal to D delta now P minus 1 C dash. This is the space of P coboundaries, and the space of cohomology, the path cohomology will be defined to be the quotient of this ZPZ with respect to BPZ. This is what we denote by the path zigzag cohomology of G with values in the representation M. Now let us maybe consider the low degree cohomology spaces. Then for H0, then this is just Z0, and it is given by all the m's in M such that the del D0 M is 0, and this 0 of M I defined before to be Px of M equals 0 for all x in G. Now, if we deal with M being G and considering the adjoint action, then the H0 is just the annihilator of G. What about Z1? Then the Z1, this is the set of all linear maps from G to M satisfying this condition. And in fact, this and H1 and B1 will be those of F such that there exists an element M, and this Fx is Px of M for all x in G. Then here, H1 will be the quotient of Z1 by B1. In fact, this is just the antiderivation, the set of antiderivations by these P derivations. And what is the antiderivations? The antiderivations, this is the set I mentioned before. But here, of course, this is maps from G to M, and they should satisfy this condition. Okay, this is the set of antiderivation from G to M, and P derivations. This is the set of F of linear maps from G to M, such that there exists an element M in capital M, such that for any x in G, we have f of x. This is Pxm. Okay, now the case of M equals G or scalars. Then here, then we recover the antiderivations of G. And we have the space of inner antiderivations. And here H1 will be just the quotient of antiderivations, quotient by the inner derivations, which gives the outer antiderivations, which will be the quotient. And now if M is K, the scalar, then this H1 is just defined in this way. And in fact, it corresponds to G, quotient by G square, and we take the dual. Okay, now let us consider the abelian extensions and the second cohomology groups to deal a little bit with extensions and also later with deformations. Then we have this short exact sequence of Jacobi-Jordan algebra. Then it is called abelian extension of G by M. In the case of we have this E, the inclusion map of M squared 0, and here P is the projection. Then as a vector space, this E, which is the direct sum of M with G, where M is a subspace, this is a G module. Then the Jacobi-Jordan algebra structure on this E is defined in this way, where C, this is is a bilinear map. Huh? Then this Jacobi-Jordan algebra we denote it by EC because it depends strongly on this C. Okay, then the equivalence between the two abelian extensions is given by the commutativity of this diagram. Huh? Then in the case where phi is necessarily an isomorphism, here, of course, this phi is necessarily an isomorphism. And we are going to denote later that XGM, the set, which is actually an abelian group of equivalence classes of abelian extensions of G by M. This is our set X, the X of GM. Then an extension defined before by this extension is called trivial if it is equivalent to the extension 7, where C is 0. 7 is the formula I have here. Huh? Okay. Then, in fact, in this case, with this E0, this is a semi-direct product of G by M. If we don't have such an isomorphism, then we say that our extension is non-trivial. Okay. Now we are going to consider some sub classes. In fact, now if I define it before the n cocycles, now if I take the intersection with the anti or the skew symmetric symmetric cochains, then I will denote by Z indexed by A here the n cocycles which are anti-symmetric. And with indicate by S here the intersection with symmetric n cocycles, huh? And what will be denoted by symmetric, for example, second cohomology here is this will be this will be the symmetric two cocycles I defined before, and here quotient by the two coboundaries. Huh? And the same for H3. This is the symmetric, the symmetric, the symmetric three cocycles, huh? Quotient by the three coboundaries. Then one observation here, if P is a representation, we consider the set Cm of all elements of M such that Px M is 0 for any x in G. Then if the Cm is 0, reduced to 0, then in this case, the second cohomology defined in general, zigzag cohomology, of course, this is the same as symmetric cohomology, zigzag cohomology here. Huh? And here we can also prove that the set of extensions G with M, this is reduced, this is equivalent to, this is defined by this H2 symmetric, huh? With respect to the zigzag cohomology. Huh? And the corollary here, we can see that the set of trivial abelian extension, this is in one-to-one correspondence with the two coboundaries. Okay, now let us discuss. Time is running. Deformations, formal deformations, and formal deformation as introduced by Gerstenhaber for associative algebra can be, of course, handled in many similarly to in many cases of non-associative algebra, but this theory introduced by Gerstenhaber, of course, relate this deformation of algebra to cohomology. That one needs cohomology. It turns out that this zigzag cohomology we defined before switches to give a deformation theory for this Jacobi-Jordan algebra. Now, what is one parameter of deformation? Here, the idea is just to extend the basic field K to the formal power series with T. And here we have a formal space, GT. Then this is a set of formal series where the coefficients are in G. Now, what we will define as a deformation of mu zero, we denote by mu zero the original multiplication here. Then this is defined by mu t, which is the sum, infinite sum of ti mu I, and mu I here are just bilinear maps from G times G to G. And this mu t should satisfy, of course, the two conditions to define the Jacobi-Jordan algebra. First, the commutativity, and then next the Jacobi condition here. And if we truncate to order n, we say that we have a deformation of order n. If we say we take n equals 1, then we say that we have an infinitesimal deformation. And now we are going to discuss these two conditions. The first condition of commutativity is equivalent to say that mu i's are always symmetric. And the Jacobi condition can be rewritten in this way here. And now we can identify the coefficients of t and get a family of equations, an infinite family of equations with respect to this p. Then for p equals 0, then we get Jacobi condition with respect to mu 0. Now, what about p equals 1? Then, for p equals 1, we get this condition, and this condition just means that d2, this with respect to the zigzag homology of mu 1 is 0. Which means that this mu 1 here is a two cocycle. But since we assume that it is symmetric, then this mu 1 should be a symmetric two cocycle. Then the first term of the cohomology is of the deformation. Sorry, this is always a two cocycle, symmetric two cocycle. Now we can discuss the equivalence between two deformations. Then we say that we have equivalence between two deformations, mu prime t and mu t, if there exists a formal isomorphism of this form, where phi 0 is the identity such that we have this condition satisfied. And this can be rewritten or can be expanded and developed and then we identify the coefficients, and for s equals 1 here, for s equals 0, then this means that since phi 0 is the identity, then it leads to mu 0 equals mu 0 dash, which is the same original operation. Nothing happened. But now if you consider s equals 1, then what you get that mu 1 corresponding to the first deformation and mu prime 1 corresponding to the second deformation should be cohomologous, which means they are in the same cohomology class. They have to be two cocycles, symmetric two cocycles, but in this case they are in the same cohomology class. Okay, then we recover the usual theorem that that only the cohomology class with respect to this zigzag cohomology is important to define a cohomology. If you take a representative, then all the elements, if this representative defines a deformation, then all the cohomologous element define an equivalent deformation. Now, if we restrict ourselves to these dual numbers, then in this case we have a one-to-one correspondence between the elements of symmetric two cocycles and infinitesimal deformation. That is the one defined in this way. Of course, we can also develop a theory to deform Jacobi-Jordan algebra homomorphism in similar way. Now, let me introduce, move to the second part, which is the conformal Jacobi-Jordan algebra. In fact, this conformal algebra comes from physics, like several structure. First, in fact, one type of algebra called vertex algebra or vertex operators algebra. This was an algebraic formalization of the properties of the operator product expansion in two-dimensional conformal field theory. They came from that theory, from physics. And the notion of a Lie conformal algebra encodes the singular part of this operator product expansion, which is in fact responsible for the commutator of two chiral fields. In fact, this Lie conformal algebra correspond to vertex algebra as Lie algebra correspond to the associative enveloping algebra. These vertex algebra were developed by Katz and some collaborator, and the structure theory for finite conformal algebra they were developed by Katz and Andrea. There is also some results about structures, and maybe one of the main results is due to Zelmanov about classification of simple and semi-simple ones. Now, what is a conformal algebra? Conformal algebra. This is a vector space A, which is equipped with a linear map partial D here, and a countable family of bilinear operations here, which we denote by this n in Z plus. And they should satisfy this condition, that there exists an n such that this A and B is 0 for all n larger or equal to this n. And we have this partial d A n B. This is minus n A n minus 1 B. And a n of dB, and this is d of A and B plus this term. Then every conformal algebra we can view it as a left module over the polynomial algebra f delta of partial d here. Then this leads to another way to express this conformal algebra. Then one can express this conformal algebra on this f partial d modules A by product by polynomial valued lambda product, which is a product from A times A into A lambda here, and defined by this sums. And this is what you call a lambda product. This here lambda is just a formal variable, and what is denoted by lambda to n like this is lambda power n by factorial n. Okay, now Then in terms of lambda product I mentioned before with these sums, one can define a conformal algebra as model A over this polynomial algebra f partial d, which is equipped by this lambda product from A times A into A lambda, such that we have this condition satisfied, which we call a conformal sesquilinearity condition. Then this is d A lambda b, this is minus lambda A lambda b, and A lambda db, this is lambda plus delta A lambda b. And we say that this conformal algebra is finite if it is finitely generated as a model over this f partial d. And the rank of this finite conformal algebra is the rank of the model. Okay, now we can also deduce some qualities, which provides from the sesquilinearity differential before. We have these conditions which are satisfied. And we can also, now we have to define what is called conformal homomorphisms. Now let us consider two f partial d models, and M and N, and a conformal linear map from M to N. This is a sequence of Fn, where this Fn is homomorphism from M to N with coefficients in F, satisfying this condition. Then in particular, the F0, this is an F delta model homomorphism. Now we set F lambda to be this sum. Then F defined by this Fn is a conformal linear map if and only if this F lambda is an F linear map and we have this condition. Okay, now we denote by C home these conformal linear maps from M to N. Then this C home, conformal homomorphism, this is an F delta module via this action. And of course, we write it in this way, but we can write it also using the lambda product in this way. And the composition now is defined in this way, or equivalently by a lambda product in this way. Now, if M is finitely generated, F partial D model, then the conformal endomorphism on M, what we denote by C and M, this is just conformal homomorphism from M to M. And this is an associative conformal algebra with the composition I defined just before. Then now, if you take the bracket, the Lie, we defined a Lie conformal bracket, and this Lie conformal bracket is defined by the following lambda brackets. And if you want the version with lambda product, it is like this. Okay, and here we can see that we can define a conformal dual of an F the partial D module M, and it is defined in this way. Then now, if we have two conformal endomorphism, then we have these identities. Now, we are going to define, in order to come back to our Jacobi-Jordan algebra and define Jacobi-Jordan conformal algebra. As you remember, we needed these antiderivations. Then you can also here define what we call a conformal antiderivation. Then a conformal antiderivation is defined is a conformal endomorphism on A, satisfying this condition. Of course, the conformal derivation is just the same with, instead of having minus here, you have plus. Okay, now what is a Jacobi-Jordan conformal algebra? Then a Jacobi-Jordan conformal algebra is a conformal algebra, a dot lambda here, lambda product, satisfying these two conditions. This is the condition which replaces the symmetry. Of course, you have to assume that's the linearity, and we have this is or the corresponding to this is the conformal Jacobi condition here. Then here, if we consider a conformal linear map d lambda, which is defined this way, then this condition here is equivalent to say that d lambda is a conformal antiderivation, like for the particular case of Jacobi-Jordan algebra, which we recover if we take lambda and mu equal to 0 and partial d equal to 0. And of course, if we forget about the symmetry here, or the conformal symmetry, this is a Leibniz conformal algebra, or if you add the symmetry, then it becomes just a commutative Leibniz conformal algebra. Now, as an example, if we start with the Jacobi-Jordan conformal algebra, Jacobi-Jordan, I was looking to the time and it's running. I hope you could allow me some extra time, Dominique. Then,
yeah, you started late, so you have say 5 minutes.
Okay, it's not that much, but okay, let's. Okay, now here this is an example. If we start with the Jacobi-Jordan algebra, then the current algebra, which is defined in this way in general, this is becomes and define the lambda product in this way. Then this is conformal Jacobi-Jordan conformal algebra, which is associated to A. And this Virasoro, Vita algebra are good examples also for conformal algebra or conformal Lie algebra. Now, if we more generally, if you start with an associative commutative algebra and the Jacobi-Jordan conformal associative commutative algebra and Jacobi-Jordan conformal algebra, then on this tensor product you can define the Jacobi-Jordan conformal algebra. This is a generalization of the previous example. Okay, now what about this Jacobi-Jordan admissible conformal algebra? Jacobi-Jordan admissible conformal algebra is a conformal algebra such that the Jacobi-Jordan conformal algebra circle lambda here, defined in this way, is a Jacobi-Jordan conformal algebra. We say that we have an Jacobi-Jordan admissible algebra. This is an Jacobi-Jordan conformal admissible algebra if this is a Jacobi-Jordan conformal algebra. Then here we recover the same example as before, but in the conformal case, then anti-associativity, conformal anti-associativity is expressed in this way. If you want the conformal associativity is the same with minus here. And the left anti-symmetric conformal algebra is defined by this identity. And both now anti-associative conformal algebra and left anti-symmetric conformal algebra are Jacobi-Jordan admissible conformal algebra, which means that this commutator or this plus commutator here or conformal commutator defines Jacobi-Jordan conformal algebra. Okay, for representations, we we have similar things. I mean, the definition of conformal model of a Jacobi-Jordan conformal algebra, then this is an F-linear map from A to the conformal endomorphism M, which satisfy this condition. Then rho, if our rho be a finite dimensional representation of a complex Jacobi-Jordan algebra, then we can define on free C the delta module C delta tensor M. This is a conformal module of the current A I defined just before. Then here P from current A to is given by this this action. Okay, semi-directed works also. If we have a conformal, an A-conformal model, and this P is a corresponding representation, then we can define a lambda product on A plus M in this way, and this direct sum becomes a Jacobi-Jordan conformal algebra with respect to the above lambda product. And this is which is called naturally a semi-direct product here. And here we can notice that M is an abelian ideal of this semi-direct product. Okay, maybe here I can say that if you have a representation of a Jacobi-Jordan conformal algebra, then we can define a dual of this, which is again a representation. The dual of the representation is also a representation in this conformal way. Okay, maybe now a few minutes.
Please, can you reach the conclusion now, because
the conclusion is that we can...
out of time.
Thank you. Sorry. Yeah, the conclusion is we can define, for example, O operators on this Jacobi-Jordan conformal algebra, which are defined in this way. And from this, of course, the particular case will be the Rota-Baxter operators in this conformal setting. And we can get all the usual construction from this Jacobi-Jordan conformal algebra with O operators like antisymmetric like left antisymmetric. We have this left antisymmetric conformal algebra, which like Brayli, if Dominique wants, anti-Brayli algebra, and we have also some nice constructions on the image. Then this again an anti-symmetric conformal algebra, and we recover all these constructions. We can also define symplectic Jacobi-Jordan conformal algebra by defining what is symplectic structure on this, and we can characterize this symplectic Jacobi-Jordan conformal algebra by and say if we have this, then we can find a compatible left antisymmetric conformal algebra. Quadratic algebra is also an interesting class, and this is when your product lambda product is defined in this way. This is so-called quadratic Jacobi-Jordan conformal algebra, and they are characterized by this Moch-Gelfand bialgebra, which are constructed by anti-Novikov algebra. Here for anti-Novikov algebra, you know all these usual constructions with and this Moch-Gelfand Dorfman bialgebra are given by two operations, and to conclude, then if we start with an anti-commutative, anti-associative algebra and the derivation, then here, of course, we can construct a Moch-Gelfand Dorfman algebra, And maybe the result is the characterization of quadratic Jacobi-Jordan conformal algebra. Here, if we have a vector space which is equipped with two operations, and f dv be the free f d modulo over f, we define this product, and this product defines a quadratic Jacobi-Jordan conformal algebra if and only if the operations star and circle, this is a mock Gelfand Dorfman algebra. Maybe I stop here. Thank you. I'm sorry.
Okay, thank you very much, Nasser. So maybe you have questions or remarks? Well, the first is the hardest one. So, yeah, no? Okay, maybe let me ask a question really from scratch, from the basics.
Yeah.
You consider a Lie superalgebra, so you have a Z2 grading,
Yes.
and consider only the odd part. Is it a Jacobi-Jordan algebra?
The old part of a Lie superalgebra?
Yeah, because the commutator now is an anti-commutator, so it starts quite well. And what about it's Jacobi with the Kosul signs? It should be quite close to this notion, right?
Ever seen this observation? Then do we have Jacobi satisfied in this case? If you take just odd elements and consider Jacobi condition, because then here, if you have odd elements, we don't have plus. We don't have plus. You should have some signs, right?
Yeah, you have a Jacobi, but with the Kosul signs. So
but here we don't have signs. I mean, it's just plus.
Okay. Okay, right. So yeah, maybe it's different.
Yeah.
Okay.
You will have signs, and then it disturb the structure.
Yeah. But yeah. But that's the case because the signs, if you have three terms x, y, and z, the Z2 graded Jacobi is Jacobi, but with -1 to the product of the two extreme terms. So for three odd terms, it amounts to ordinary Jacobi. So yes, it makes sense.
Okay.
Okay. Alberto, the product of two odd elements is not odd. Yes, yeah, of course, that's right. Sorry. Yeah, of course. Thank you. Okay. Okay, that's right. Sorry for that. Okay. So are there other questions? Okay, so I could have a vague question. Do you have Lie Jacobi groups the same way you have Lie groups? The Jacobi-Jordan groups, sorry, in some sense.
Yeah, but it means that, but here you need some. I don't know. Good question.
Okay,
yeah, but what will be the structure? Is it a group structure? I don't know. Maybe something different. I don't know.
I don't know, but you know that you obtain
if you take
by some, yeah.
If you take Leibniz, for example, then it's you have this rake.
Yeah. And this
but maybe with some
yes,
special
yes.
rake, you can get something. I don't know. But,
So the same way
but for sure, not groups. I think.
Yeah, you get a Lie algebra by somehow twice differentiating a Lie group. And yeah, okay, maybe there's a structure to be found there. I don't know. Okay. Are there other questions or remarks? So if not, thank you very much to the speaker again. And
thank you.
and see you to the next talk. So next week, I guess. Okay. Thank you very much.
Thank you.
Bye-bye.
Bye-bye to everybody. Thank you.